Today we're going to talk about dimensionality reduction in the context of machine learning. We're going to discuss a variety of methods for dimensionality reduction. They include principal component analysis, or PCA, feature selection or feature elimination, factor analysis, and linear discriminant analysis, or LDA. You probably have come up with a variety of questions that include things like, how do I deal with high or very high dimensional data? That is big data. Or how do I pick the features, that is independent variables, that are most important to my analysis? This is closely related to how do I improve the performance of my machine learning methods? And that gets us back to what machine learning is all about. That is, improving performance is actually learning in the machine learning world. Now, PCA has been around for over a century now. It was first introduced in 1901 by Carl Pearson. Pearson's a pretty famous guy, you know. He was a mathematician, a biostatistician, and is actually credited with establishing the discipline of mathematical statistics. He founded the first university department of statistics at University College London in 1911. In the 1930s, it was reintroduced by Harold Hotelling and named PCA. Hotelling was an economist. Besides his work on PCA, he developed Hotelling's t-squared distribution, which is a generalization of the student's t statistic that we've used in multivariate hypothesis testing. PCA has other names depending on the field of application. For example, the discrete Karhunen-Loewe transform, KLT, in signal processing, the Hotelling transform in multivariate quality control, singular value decomposition, SVD, of the matrix X, as done by Golub and Van Loan in 1983. Eigenvalue decomposition, or EVD, of the X transform X in linear algebra operation, and in factor analysis, and in spectral decomposition, in noise and vibration, and in many, many more. Conceptually, PCA is used to identify the axes that explain the greatest portion of the variance in a data set. Now, I've said before that if an instructor repeats something, you know that that particular concept is important. So let me repeat that sentence. PCA is used to identify the axes that explain the greatest portion of the variance in a data set. Okay? PCA actually identifies all the variance in the data and labels the corresponding orthogonal axes, PC1, PC2, PC3, etc., where PC1 has the greatest variance, PC2 has the greatest portion of next greatest portion of variance, and so on. Some classify PCA as an unsupervised learning technique because it finds patterns in the data. That is, it finds the portions of variance along orthogonal axes. For example, if you are conducting an analysis and you want to reduce the dimensionality of your data set, you could use PCA to do this. You conduct PCA to determine which axes explain the variance in the data to the level of accuracy you want, or to the number of dimensions you want, or that generate the machine learning model with the best overall performance. So PCA focuses solely on identifying and preserving the variance in the data. As an aside, using PCA to decorrelate the dimensions in a data set can make optimization algorithms you might use later run better or faster, and that's in addition to dimensionality reduction. However, PCA doesn't necessarily get what some would call the most important features. That is, there may be features that contribute or represent, is probably a better word, a relatively small portion of the overall variance, but that are an essential part of qualitatively explaining something in the analysis. So feature analysis, another alternative, or feature selection, will select the best by some criteria from the set of features, but not necessarily those features that explain the largest portions of variance in the data. Proponents of feature selection claim that they are developing the most understandable model. An example of this would be classification. If feature selection is used, then a classification algorithm run, then if the feature selection was done properly, you should get a lower error rate in the classification than you would just running an entire data set. That is, then in this case, the feature selection has eliminated extraneous features. What about factor analysis? How does it fit in all this? Factor analysis is another technique that is used to analyze variability among features. However, unlike PCA that studies what generates the greatest variance, or feature selection that selects the best based on some criteria, factor analysis is a statistical method that looks at shared variability. So factor analysis is really quite different than PCA. To really understand factor analysis in terms of factors, you need to know that a factor is something very different than a feature or a variable. For example, in a Bayesian network, a factor is a subset of the entire set of variables. Factor analysis is typically used in analyzing relationships in complex concepts. So you might use factor analysis to analyze very complex situations, things like socioeconomic status, dietary patterns, or intelligence. Let's consider an example. Let's look at socioeconomic status. One of the key concepts in factor analysis is that multiple observed variables has similar patterns of responses because they are all associated with a latent variable or latent variables. It is variables that are not observed or directly measured. So in our socioeconomic example, we can observe and measure income, education, occupation, home value, number of public parks in the neighborhood, number of violent crimes per year in the neighborhood, and so on. All these variables are associated with the latent variable or a latent variable in socioeconomic status, which is what we're trying to analyze. Once we have our data, we turn again to eigendecomposition. For factor analysis, an eigenvalue is a measure of how much of the variance of the observed variables a factor explains. For example, if we performed an eigendecomposition on a factor with 3 variables, say we combine income, education, and occupation, combining those 3 variables, and we found an eigenvalue of 2.3, then that eigenvalue explains a relative proportion equal to 2.3 of the variance of those 3 combined variables. We'll talk more about factor analysis later. Before we get into the slideshow, let's talk about one more type of analysis, linear discriminant analysis, or LDA. Remember that Ronald Fisher is another really famous guy. Fisher is credited with being the genius who almost single-handedly created the foundations for modern statistical science, and the reference on that is Anders Hald in 1998. You might remember from another discussion that Fisher's daughter married George Box, who developed the Box-Cox transformation. So interesting family relationships and knowledge. Anyway, LDA is a generalization of Fisher's linear discriminant, which is a method used to find a linear combination of features that characterizes or separates two or more classes. Let me say that again. LDA is a generalization of Fisher's linear discriminant, which is a method used to find a linear combination of features that characterizes or separates two or more classes. So LDA deals with this issue of dimensionality reduction in a completely different way from PCA, which seeks to preserve the variance in the data. Let me put this another way. Where PCA finds the directions with maximum variance, LDA is used to find the directions that maximize the separation or discrimination between different classes. LDA is closely related to ANOVA and regression analysis in the sense that ANOVA and regression analysis can consider how a dependent variable or response is a linear combination of independent variables or features. LDA is also closely related to PCA and factor analysis in the sense that they all look for linear combinations of variables that best explain the data in some way. For LDA works best with continuous variables when the variables are discrete. Use discriminant correspondence analysis. Let's get into the slideshow. And I've labeled this lecture with the names of the methods PCA, feature selection, factor analysis, and LDA. To indicate that it's really a lecture about these methods. We'll start with principal component analysis, or PCA. Then we'll look at feature selection, then factor analysis, and lastly, linear discriminant analysis. It turns out that each of these techniques, not feature selection so much, but each of these techniques depends in some way on eigendecomposition. So before we begin looking at these specific methods, we'll review eigendecomposition and look at some examples. Let's quickly run through these slides just to refresh your memory. And before I get into this particular slide, I want to talk just for a minute about the motivation to learn about eigendecomposition. Eigenvalues and eigenvectors play an integral part in the analysis of linear transformations. Eigenvalues and eigenvectors originally were used to study the principal axes in the rotation of rigid bodies. In the 18th century, Euler discovered the importance of principal axes in the rotational motion of a rigid body. Then Lagrange realized that these principal axes are the eigenvectors of the inertia matrix. And the mathematical development has continued to today. Today, they are also used in stability analysis, vibration analysis, facial recognition, matrix diagonalization, and much more. You can look up online if you want. To start with Wikipedia, use the references in Wikipedia And those references will point you to a lot of information about eigenvalues and eigenvectors. I want to talk about this, and it's a little bit difficult because it's not on this particular slide, but what you're going to find is that eigenvectors are principal vectors. As something is stretched or skewed, think about the image of the Mona Lisa. As it's stretched or skewed, if it's a principal axis, it's not going to stretch and it's not going to change direction with any matrix that's applied with it to skew it. If it's not a principal vector, it could be stretched, it could be skewed, it's going to change. And that's what we're going to try to demonstrate with this background information. So consider a simple example of eigendecomposition. An eigenvector is a non-zero vector that satisfies the equation A nu is equal to lambda nu, where A is a square matrix, lambda is a scalar, and nu is the eigenvector. We've already looked at individual pieces of this. Note that lambda is called an eigenvalue. Eigenvalues and eigenvectors are also known as characteristic roots and characteristic vectors, or latent roots and latent vectors. You can solve this the same way that we've solved matrices before when you also account for lambda. Here's an example. Consider the matrix A is equal to 2, 1, 1, 2. Remember that Hefferon, H-E-F-F-E-R-O-N, Hefferon's textbook is online. His example of this is example 3.7, which is a 3 by 3 matrix that he's called matrix T. We're just going to use this simple 2 by 2 example for us. Now, if we insert the matrix A into our equation A nu is equal to lambda nu, and we got 2, 1, 1, 2 times x1, x2 is equal to lambda x1, x2. And if we expand this out, then we get 2x1 plus x2 is equal to lambda x1, and x1, 2x2 is equal to lambda x2. If we solve for lambda x1 and x2, then we're going to get 2 minus lambda times x1 plus x2 is equal to 0, and x1 plus 2 minus lambda times x2 is equal to 0. And this gives us a matrix of coefficients in standard or canonical form. This is in Hefferon's textbook in matrix form at the top of page 400. The trick is that for this system to have a non-zero vector x1, x2, the determinant of the coefficient matrix must be 0. And that is, we have a matrix of coefficients of our equations as 2 minus lambda, 1, 1, 2 minus lambda, and the determinant of that has to equal 0. So if we set that equal to 0 and solve, the 2 minus lambda times 2 minus lambda minus 1 times 1 is equal to 0, or lambda squared minus 4 lambda plus 3 is equal to 0, and then you continue solving. There are two values of lambda here that represent two eigenvalues, and they satisfy this equation. Lambda 1 is equal to 3 and lambda 2 is equal to 1. Eigenvalues can be considered to measure strength or relative length in the n-dimensional space where eigenvectors have both direction and magnitude. Eigenvalues are simply the strength or magnitude. You can refer to Heffron's for his three-dimensional example. If we plug lambda back into the original equations to find the corresponding eigenvectors, that's 2 minus lambda times x1 plus x2 equals 0. For lambda 1 equal to 3, then solving the equation, we get x1 is equal to x2. For the lambda 2 equals 1 equation, when we solve, we get x1 is equal to minus x2. For each eigenvalue, there will be an eigenvector. However, while an eigenvalue represents a magnitude, such as the length of an axis, the eigenvector determines its orientation in space. Therefore, the values in an eigenvector are not unique. For the example we've been studying, lambda 1 equals to 3, we found that x1 equals x2, but we could also say that 2x1 is equal to 2x2, or 5x1 is equal to 5x2, and so on. Now, I encourage you, if you're not following this, to go back and solve these equations, expand everything out, and make sure that you can get those solutions. So this is this same matrix and these eigenvalues and eigenvectors in R. As usual, there are several packages we can use, and they have slightly different syntax for the commands. But we're going to take sort of what's the middle ground for now. You are going to use a package rcpp eigen. For more information, you can look that up online. The R snippet is shown on this slide. First, we enter the matrix A. Then we use the eigen command to find the eigenvalues lambda 1 and lambda 2. We display them and see they're exactly the same values that we got when we calculated by hand. So we check to ensure that the determinant was 0 using the det or determinant command. We can also check and see that the Euclidean length of x equals 1. But there is one more thing we can easily do in R that we didn't do by hand. We can find the actual eigenvectors for this problem. We just use the vectors command to do so. This is also shown on this slide. Remember that these eigenvectors are the principal axes for this system. So you can see the matrix of the eigenvectors. So this is the complete solution to this problem for an n by n matrix where n is equal to 2. It's a 2 by 2 matrix. Number of dimensions is 2, so that is there is 2 eigenvectors, and they're both shown on this slide, and it's all really pretty straightforward. Let's go to the harder problem of principal component analysis. We'll go through all the steps we'll use to conduct a PCA. PCA is not what is called scale invariant, so one of the first things to do in conducting a principal component analysis is to standardize or normalize the data. We saw this in regression 2 when one or more of the variables scale is much bigger than the others. That variable can overwhelm the smaller, the features that have smaller scales. So the example that I used in conducting a regression analysis was the housing data that we used where home values were in the hundreds of thousands of dollars, but the number of bedrooms was typically single digits. So you can see that the scale varies greatly. that we scale or normalize the data to prevent this or to get a realistic, reliable result. I also need to briefly remind you that I've said that all this is leading to singular value decomposition, or SVD. It turns out that SVD in linear algebra, and I'm just going to quote here, that the singular value decomposition, SVD, is a factorization of a real or complex matrix. It is the generalization of the eigendecomposition of a positive, semi-definite, normal matrix. For example, a symmetric matrix with positive eigenvalues, to any m by n matrix via an extension of polar decomposition, and so on. The quote continues. So SVD is used for solving homogeneous linear equations, that is, solving systems of linear equations when they are equal to 0 are homogeneous. Total least squares minimization, signal processing, quantum information, numerical weather prediction, recommender systems such as those used by Amazon and others, disease for surveillance, and natural language processing all use this. I said that this was leading up to SVD, and we won't actually go over SVD right now. What I want you to know is that it is only one more step to get to SVD. So when the time is right, you can use the information that we're going through in this lecture and make that one more step and use SVD also. For example, once we've standardized or normalized our data, then we'll conduct an eigendecomposition. The reason I brought up SVD is because since it is a generalization of eigendecomposition, it's also one way to conduct an eigendecomposition. It's another way to get eigenvalues and eigenvectors from the covariance or correlation matrix. Once you have your eigenvalues and eigenvectors, you will sort the eigenvalues in descending order and choose the number that represent the number of eigenvectors that you need to use in your problem or your analysis. And those generally correspond to the largest eigenvalues. So let's let the lowercase k matrix represent the number of eigenvalues selected. So for example, you might select 2 or 3 or how many ever. If you've decided that the level of accuracy you need to have, you're going to need to account for greater than 90% of the variance in your data, then your lowercase k matrix of eigenvalues will include all of the eigenvalues that add up to at least 90%. If you're going to be working in 2D, then select the two largest eigenvalues and their corresponding eigenvectors. That's both ways are straightforward. If you're going to be working in 3D, then you'd select the 3 largest eigenvalues and so on. So there are different ways to look at this, by percentages, by the number of dimensions you want to work in. In most analyses, you will wind up selecting a sufficient number of eigenvalues and corresponding eigenvectors to adequately model your data. I mentioned 2D and 3D because those are things that are easy to visualize on paper. Just because we can't really visualize beyond, say, 3D or 4D, it doesn't mean that we're going to stop there. We're going to pick the number of eigenvalues and eigenvectors that are needed for the level of accuracy we have to have in our analysis. However many you pick will be the dimensionality of your analysis. In linear algebra terms, this will also be your new feature subspace. Once you have the eigenvectors, you can construct the projection matrix from the selected eigenvectors. Now let's call it capital W, and the W is highlighted or bolded because it's a matrix also. Again, if the dimensionality is low enough, we can actually draw the projection matrix out. Otherwise, we'll have a numerical matrix to work with. Last, we'll transform the original data set, X, via W to obtain a k-dimensional feature subspace, Y. So that's the last sentence on this slide. And let me say it again. The last step is to transform the original data set, X, and that X is in bolded to indicate it's in a matrix, via W to obtain a k-dimensional feature subspace, Y. Summarizing the whole process, the first step is to standardize the data. The second step is to obtain the eigenvalues and corresponding eigenvectors. The third step is to sort the eigenvalues in descending order and select k, the number that you're going to use for your analysis. The fourth step, you're going to construct the project matrix W from the selected k eigenvectors. And then last, you're going to transform the original data set X via W to obtain a k-dimensional feature subspace, Y. And that all seems pretty straightforward. One additional thing you can do is to plot 1 minus R versus the number of components to visualize the number of principal components that retain most of the variance in the data as you're going to create your projection. Alternatively, you can do a histogram or a bar chart, etc., to determine this if it isn't obvious already, if you're not working in a small enough subspace, 2D or 3D, that it's obvious. Let's look at a specific example, and I'm sure that will help make all of this linear algebra and concepts that I've presented to you much clearer. Let's look at the iris data set. It's a classic example. We've used it before. We'll use it again. Let's perform a principal component analysis on it. And I'll do this in R and in Python. We'll look at the R code first. Most of this is taken from the reference at the bottom of this slide from R bloggers. The code is pretty self-explanatory. First, we're going to load the data, then perform any pre-processing, for example, standardization or normalization. The reference says that Venables and Bryan in Modern Applied Statistics with S+ recommend taking the log of the data. What Venables and Ripley actually say is that if the data are physical measurements, that's a good initial strategy to work on a log scale. I did the analysis taking both the log of the data, and I did the analysis without taking the log of the data. And for the iris data, it looks to me like the analysis is actually better not taking a log of the iris data, so that's what I'm presenting. Notice, that I left the data object used to store the input data, log.ir, even though I'm not actually taking the log of the data. This is just so I didn't have to go through the entire code changing a data object name again and again and again. Notice that We're still using the PRComp command to center and scale the data, even though I'm not taking the log of it. And we're going to use the PRComp command to do the actual PCA and print it out. Now, SVD, it turns out, is the default method used to conduct a principal component analysis with the PRComp command. If you use PRIN, PRINComp, the default method is the eigendecomposition of the covariance or correlation matrix. We plot IR-PCA, that is the variances, as a function of principal components. One last thing I need to mention is that there are a couple of tests that provide some guidance on which principal components to keep. One is the Kaiser criterion, developed by Kaiser in 1960. Kaiser says to retain only factors with eigenvalues greater than 1. That is, unless a factor extracts as much as the equivalent of one original variable, you should drop it. The second test is the Scree test by Cattell in 1966. According to Cattell, you should find a place where the smooth decrease of eigenvalues levels off. To the right of this point, we find only PC Scree, meaning principal component fragments. I've included a Scree plot on the following slide. Looking at the plot on this slide, I'll fudge a little and say that the second principal component is about 1 and plan to keep PC1 and PC2. And I've included a bar plot of IRPCA2. It really provides the same information as the line plot. Next, we print out the summary information, and this gives us the standard deviation, portion of the variance, and cumulative portion of each principal component. In order to actually generate a Scree plot, you'll need to install another package in R. You'll need the Facto Extra package, which you can get from GitHub as shown on this slide. This actually installs a bunch of other packages as dependencies too. Once you've installed and loaded the Facto Extra package, the command to generate the Scree plot is fviz_eig. So on this plot, you can see by the scale on the vertical axis the percentage of explained variance. The first principal component, just denoted by 1 here, is roughly 73%. The second principal component, 2, is about 21.5%, maybe 22%. So the combined total of those gives you over 90% of the variance in the data. So you would probably consider the principal component 1 and 2 enough for your analysis. All this is fine, but I would have to add up the values, like I just did, of the individual components to see how they are trending. So I like to look at a slightly different plot. I like to look at the cumulative proportions. So I've used some different information to plot this. From this line plot, you can easily see that the first two principal components include over 95% of the variance in the data. You could put some lines from the tick marks across this, but I think you can see it okay. We can use the predict function for new observations then to see how new observations fit in the principal components we've already found. The author of the RBlogger webpage I've used likes ggbiplot as a plotting package, so I've installed that as well and used that to create the last plot. And this is particularly interesting. Before I put up a really interesting plot, though, to finish off this R code, I am including the alternative method presented using the caret package, caret spelled C-A-R-E-T. This function's default is to keep only the principal components that are necessary to explain at least 95% of the variance in the data. Even so, the eigenvalues seem slightly different, and the overall analysis produces the same answers. So I like to keep the first two principal components. Now to the interesting part. First, I followed the prescribed method, that is, published by our bloggers. This method keeps the entire data set together. All three species of iris. It centers and scales it all together. And if you look online, you'll find that that is almost 100% of the time the way that it is done for the iris data set. By doing this, the differences in size between the Setosa and the other species are really ignored. Setosa are actually about 1/4 the size of versicolor or virginica. So we get principal components that preserve this variance, this difference. Note that the Setosa, as shown by the red data points, is really separate from the data points for the other species. And I'm going to ask you if that's the correct way to do it. You need to think about that. It depends on what you want to get from your analysis. What I'm seeing in this PCA is that the reason most of the variance in PC1 is due to the Setosa species actually being much smaller than the versicolor or virginica species. So you see the amount of variance that's recorded horizontally. If we really want to know the variance due to the four features, shouldn't they be on the same scale? And what I mean is, should we have normalized the species to be all on the same scale? So the next couple of slides, I'm going to take a look at that. Our summary data, when we keep all the species together, is shown at the bottom of this slide. The importance of the components PC1, PC2, PC3, and PC4 are shown by the portion of the variance. So PC1, like I said, it's about 73%, and PC2 is an additional 22.5 or 23%. Here's a picture of the various species, and you see these pictures a lot, but I've modified the size of these pictures, and it makes all the species appear to be roughly the same size, but again, they're not. Remember that the Setosa is about 1/4 the size of the versicolor and virginica. So my question for you is, what's really the right way to do a principal component analysis on these species? By hand, I found the mean of the Setosa species for each of the four features and normalized the Setosa data with that value, the mean of the Setosa alone. Then I found the means of the versicolor and virginica species and normalized them with that data using their means. It really makes a difference. Here are plots of the normalized data. Notice that all these plots are all on the same scale now, so that you can visually compare them apples to apples. You have to manually set the limits for the y-axis, as you often do. You can't just let it auto scale or things begin to look different. It can be very misleading using auto scaling. Anyway, you can see across all 150 data points in the iris data set, there isn't much variation in sepal length or width. There's more variation in petal length, but the big variation is really in the petal width. Here is a comparison of the principal components found the way we did it originally, with all of the species consolidated as a group, and then with each of the species normalized individually. As expected, the petal width is the feature mostly in the same direction as PC1, which accounts for over 80% of the variation in the data. So that's a big difference. Now we've accounted for over 80%, 0.8138 of the data with the first principal component, where before we only accounted for 0.7296. So it's roughly 10% more. And correspondingly, the values of PC2, PC3, and PC4 change. So the point that I'm trying to make, if you look at this, the images from the principal component analysis actually look very different. But in the end, it gives you the same answer, roughly, for your overall analysis. If you didn't know if you didn't know your data set as well as the iris data set, this might be something that gets lost in your analysis. I'm just saying you need to think about what you're doing. So let's move on and look at the Python version. I've included the code for the Python version here. And it's actually that I've copied the Jupyter notebook. And I followed the example that's referenced at the bottom of the slide here. As before in R, we have to load the data set and conduct our pre-processing. So this is a bit different from the analysis in R. Here we're setting up to plot histograms of the 4 features. So that's interesting. And there is a plot using the 4 features. Although the units of measure are the same, unfortunately the scales on each histogram is different. So the output from Python more or less auto-scaled. So don't just visually consider these. Look at the differences you can pick out. For example, the petal width that we found the greatest variation in before shows that the setosa varies by somewhat less than a centimeter, whereas the virginica varies by almost 2 centimeters. Here we're following essentially the same procedure as the first example in R. That is, we're standardizing all the data for all the species all together, and then we perform the principal component analysis, actually 3 ways, beginning with an eigendecomposition on the covariance matrix. Now we go do an eigendecomposition on the standardized correlation matrix, and then we do an eigendecomposition on the raw data based on the correlation matrix. Notice the values of the eigenvalues, that is 2.9108, 0.9212, 0.1474, and 0.0206. And again, 2.9108 divided by 4 equals 0.7277. That is, the eigenvalue with the highest value comprises 72.8% of the variance, which will be shown on a graph in the following slides. So it matches the output from the R, but we have to do a little bit of translation on the output from Python to get to those values. Here's the rest of the code in Python. We do an eigen decomposition for the principal component analysis using SVD, which is actually the currently preferred method and the default in many software packages. And we see, as we did in the R example, that the results are the same regardless of how we made the computation. As I've said before, this is an old and still a very good way to check to make sure your code or program is working correctly. If you use exactly the same data set and you're doing an analysis, you should get the same answer regardless of the code or program, given some slight differences for rounding, etc. So here are some of the results. As before, the first two principal components have nearly all of the variance. So here you see a cumulative proportions plotted over the bar plot. And so that's a nice way to visualize the results of the analysis. I want to compare all my results, so I've put both the output from the Python code and the original figure from the R code on this slide. Because the process we used in Python followed the same logic as the original one in R, we get virtually the same results. The color changed just a little bit. Instead of Setosa being red as it was before, now it's blue. Versicolor is orange rather than green, and Virginica is green rather than blue. So there's a little variation in color, but when you look at the figures, they're pretty much the same. Because the process we used in Python followed the same logic as the original one in R, we get virtually the same results. The Setosa, being a smaller flower, generates most of the variance in the data and is reflected in PC1. So I would argue that what we essentially did was a principal component analysis on the iris species as groups, so between groups, as much as we did on the 4 features included in the data. So if you know something about design of experiments and you know about having various treatment groups, then that's what I'm saying. The variance is really between groups rather than between variables. If that's what your principal component analysis is intended to do, that's fine. But if we really wanted to see what the principal variation is in the 4 features, sepal length, sepal width, petal length, and petal width, then we need to normalize the data properly to get that. And for the last few slides here on principal component analysis, I wanted to show you an alternative method in Python you can use with the package sklearn. So that's shown on this slide. If you do this, you'll find the same result as we just got using a longer Python code. So what do we know now? We can use principal component analysis to dissect and rank the correlational structure of multivariable data. So to work, principal component analysis needs some variable correlations. We can use principal component analysis to reduce dimensionality of a data set by finding the best lower dimensional representation. That is, we can use PCA to reduce the number of variables of interest into a smaller set of components. These components are linear combinations of the original variables. So this is accomplished by analyzing all the variance in the variables and reorganizing it into a new, smaller set of components that is actually equal to the number of variables that exist. However, these components are aggregates of the variables, and we can select which of these components we want to keep. That is, those that represent most of the variance in the data. The first principal component is a linear combination of the variables that maximizes the component score. The second principal component extracts the maximum variance from the residual matrix left over after extracting the first component and is therefore orthogonal to the first. The new components are independent and orthogonal and explain all the variance in the data. So they're indeed principal components. You can't skew them. You can't change the magnitude of them. They are principal components. Right now I'm going to stop the recording for the first part of dimensionality reduction, our discussion of PCA, and I will continue recording with a part 2 and begin with feature selection.